I should like provide you some kind of midterm quiz, and then we just have a break for a week, and then we come back and start the external force convection. But then I just feel that I should teach you this. I don't know why, but I think we waste too much time. Sorry. I'm sorry. But yeah, I think we a little bit like lag behind the plan. Something like that. But not so sure. Haven't checked carefully, but everything is fine. Still in my hands, so you can believe me. Okay. So we have 20 people at this moment, which is I still cannot remember like how many people like register into this course. Okay, so it seems like 29, right? Let's wait a bit. Yeah, but so yes, because it's your holiday next week, I won't give you any homework, but then we will back on our track again next week. Okay, no, not next week, next 2 weeks. Okay, so I hope you really enjoyed this period. That you like have a break, go watch movie. You cannot do it at this moment in Thailand. Go somewhere else. Go to Khao Yai, Tori. Spend time with your friend. I don't know what you plan to do in a holiday. For me, it's all about preparing the what to teach, and there were so many things that I need to do, so I cannot go anywhere. This is so sad. I'm not sure. Like I heard like a lot of students complain, especially in Twitter or some like kind of social media, that probably articles also like assign some works for you guys to do, and then how come that they are holiday? They are not, right? It's not a holiday at all. So yes, but then one thing. Let's wait a little bit more for your friend, so I will talk just a little bit more. I just experienced on, I think, yes, this Monday that I held a class of probably 500 students in Zoom. It was my first experience, and it's totally a mess. Because like everyone just like if they have question, they will keep like texting on the chat box, and then I can't even read the first one. Then the next one came up, and there was so many comments, so many questions, but it was one. There were so many interaction with students. I'm not sure, but probably because they are young, so they like just graduate right from high school, and they already like have experience in studying through online platform since they were in high school. So they kind of enjoy, not sure, because a lot of complaint was going on in Twitter, but I think they kind of enjoyed. And so it's totally different with like fourth year student at this moment. They were too old already. So, but life is like this. So we need to like find some positive thing and enjoy with it. We cannot change our life. No, we cannot change the world, but we can change our life, right? So just a little of modification in our perspective would help us to enjoy our life. And I think this is a key as well for learning something. So I just need you like with a little bit of modification to enjoy the course, to enjoy this course. And I really hope that the content would be fun for you. For last time, like in chapter 5, I think, chapter 5, so numerical method, I really understand what you are facing, what you feel, but trust me, to understand it too roughly, you just need to tackle the problem. Quote of the day. Okay. But yeah, you need to tackle the problem, and you need to do step by step, try to create a program. Maybe have a look at the program that I already provide. Try to compare the idea step by step, line by line, and try to think what is happening in this line. It takes time. I admit it. And I can understand that because in SUT we study trimester, right? So there were a lot of things going on, and yeah, but it takes some time. If you enjoy, you still have to face it in few subject after this, like CAE. We have 2 course of CAE, right? Yeah, it would be a problem if you don't start tackle the problem at this moment. And also, I just want you to think this is my intention for all the time, starting from ME Math 2. The idea of using numerical method is just that we have very simple equation, but there were too many equations, so we cannot just solve it by our hand. It takes time. It's not difficult, but it takes time. Difficulty and time consuming is 2 different things. So we have to distinguish it. And in this case, it's time consuming. It's not difficult. So it's not like solving a puzzle. Sometimes you solve the puzzle, you cannot solve it, right? But that is difficult. Solving a Rubik like that. But this is something different. It's just time consuming, not difficult. So now we are in the world, we have so advanced technology. I think 2 days ago, one student come up and they asked me how to solve this equation. They do their how to say, the senior project with me, and it's just this kind of equation. Let me just show you. It's not so difficult, but let's say something like this. Yeah, it's something like this. And they ask me how to solve for the x. I tell him. So he is a group of 3, right? To make a electric bicycle. So he cannot solve this equation. He said he tried. I said no. You should think out of the box, because this is just to get the job done. It's not that you like have to submit how to solve this to me because it's the exam. No, it's not like that. You have a lot of like software on the internet, and you can just like apply this equation, right, into that software and solve for the x, something like that. And then he like take a little bit of time, submit it, put it in the software, and then he came back. He said that they provide me an answer, but I don't know how to interpret it. I just want one value, but they give me the answer as a function of n, something like that. And it's all because the sine and the cos, right? It's the wave. Then the intercept between the two is not just one value, but it will came back periodically. And at that point, I don't really understand why they don't understand that, because it's the sine and cos. And yeah, but in the end, what I want to tell you is that we advance so much. Sometimes solving the equation should not be your problem, should not be the main problem for you to understand how numerical method works. If you can understand what numerical method and how numerical method works, that is, I would like be really appreciate for that. But if you don't understand, I just want you to like consult with me, talk to me. I will try to give you an advice, but then again, you need to put some effort in order to learn something. I think, of course, like learning from like hearing some other people talk to you, explain to you, it's really helpful. But then again, learning by doing is much more, how to say, that kind of knowledge, that kind of the feeling that you are learning will stick into your mind for the rest of your life. No, not really, but for a long time, something like that. So I really hope that just do it. And if you don't understand anything, just come and ask me. So today we will, yes, the slide should provide to you. Wait a second. The slide. This one. Lecture. Chapter 7. We still have chapter 8, 9, 10, 11, 12, 13, I think. So probably 5 more. So if we keep our pace right, I think we are on the track. Okay, please download their slide. The content today, I don't think is difficult, but it contains so many this kind of equation. Looks complex. I don't think you would like this kind of equation. Seem not a good equation to remember. And you don't need to remember. Most of the time, when we face, talk a bit about the heat transfer in my bachelor study. So we don't really need to remember this kind of equation because it's not that important. It's not that important to remember it. It's not like F sigma F equal to MA is not the Newton first law, second law, whatever. But it's the kind of empirical So this is the formula you obtain from experiment. And if you can remember, I think I have ever give you a, like some exercise in MEMAT to fit the experimental result to this kind of equation to obtain for the exponent, obtain for the coefficient here. And it's all obtained from fitting. And if you can like link your idea from MEMAT2, you will know that this is the regression analysis. And they obtain this equation like that. I will talk more a bit about them, but just leave it here at this moment. I think you don't need to remember it because it's from experiment, and there were so many empirical formula out there. And in this book or in this lecture, we just pick a few of them and introduce to you to make you be able to know how to utilize it. Not really important about the number or the number, okay, this is to the power of 1/3, something like that. No, not really important. Because if you let's say you do the research, you get into your master study, PhD study, sometime you will be the one who create this kind of relation and publish to the public, something like that. So studying in master degree or PhD is about providing some solution to the public. And this is one solution that they found. They obtained from a careful experiment and try to help you who don't have the experimental apparatus with yourself, right? To be able to do some analysis, to be able to carry the analysis about the heat transfer. And it's very unique to how to say, it's very unique to the problem. Like this is the flat plate with an heat starting length. So this equation work only to this kind of problem. You cannot apply it to something else like cylinders. No, not like that. And it's all because we try, as I mentioned, in last session, in previous session, that heat transfer from convection is way too complex. It's very complex, right? So you cannot describe the convection easily. Also, we try to simplify everything into a Newton law of cooling, but then it further complicates other analysis to obtain the edge. And here is the relation that you want to obtain the edge. So, okay, in the end, we have a very simple equation, HA delta T, to calculate for heat transfer, but then we complicate it by having this kind of relation to calculate for the edge. So it is how it is. A very simple analysis was done in this way for the heat transfer problem. So basically, when I talk about the PhD or master study and we propose some kind of equation like this, it's because at first when I became a PhD student in Japan, my professor told me to create one of these. Basically, it is like that. He told me to create it, but then after a few months into that kind of research team, I found that before we get into this kind of relation, there were so many problems, and I want to solve it. So I suggest to him, and then the research team like diverged in another way. So yeah, still it's really popular if you want to like study in master or PhD student. Maybe like one day, for 50 years after this or 100 years after this, your your surname will be on a book like this, and everyone would know that okay, this is the relation from, I don't know, who should I call his or her surname now? Okay, let's say like it's a Suryo relation, something like that. So maybe you want you to register your name into the book. I don't know. Okay, so let's come back to the topic that we want to learn today. So it's external force convection. External. So it's not internal. It's opposite thing. You may know the external flow, right? So here we deal with the external flow and together with force convection. So that's why we called it external force convection. So basically, the real life application that we can think of at this moment would be turn on your fan and put it against you. There will be a wind or a wind like fall through you, right? So that is force convection, and it's the external flow over your body. Okay, let's do it. So what we want to learn from this chapter is that at first we should be able to distinguish between the internal and external flow. I don't think it's so important for you guys because you already learned fluid mechanics, right? And fluid mechanics that you learned is just last semester. So I'm pretty sure that you know what is internal, what is external flow. And I think like based on previous session, I understand that you kind of still remember really well about fluid mechanics because there was no question at all. So I will like talk about it like just a little bit. And maybe the objective is also to intuitive understanding of friction deck and pressure deck. And then if you look at the average drag and convection coefficient and external flow. Okay. This is very close to fluid mechanics. And then we evaluate the drag and heat transfer associated with the flow over the flat plate for both laminar and turbulent flow. Okay, here we deal with heat transfer already. But we consider only a very simple case, a flat plate. Oh, who care about the flat plate? Why don't we learn about the flow over the airplane that fly with the speed like higher than the speed of sound? So really high Mach number. And then it will generate heat over the airplane. Yes. That problem is very complex. And I think it's kind of a topic for a lot of PhD students still in this moment. We for those students who like have strong relation with NASA, they would like have to study about the material that you use to construct the airplane. Not really airplane. What should I call it? Is kind of a spacecraft. So yes, very important still. drag and heat transfer, still very important subject or very important course in mechanical engineering. Then we will leave these two, which is drag force and the pressure drop and heat transfer with the flow across the tube bank. We will leave the last two for the next session. Okay, so now let's start. We know that we encounter or we face a lot of flow that flow over the body. It's very frequently occur in practice, and in such case, we have drag force. We have to face a drag force. We are facing something like a lift force, which is the upward force that make the airplane can fly. Okay, and then it's this kind of application of the knowledge of heat transfer or fluid mechanics is very difficult. Not only because the geometry is complex, but still there are involvement between 2 or 3 cores together, and makes the problem very complex. But then, as you can imagine, in this kind of geometry, how could you let's say make analysis using of course you need to use the numerical experimentation, right? Because let's say if you do the real experiment, you need to create the airplane, maybe like a smaller size, but still you need to create something and do the experiment. And you need to have the experimental apparatus to do like that. And that is kind of costly. So most of the time at this moment in the history, we use numerical experimentation. So apply the knowledge of, again, numerical simulation to conduct the experiment. I think maybe you did it in the ME Lab 1, right? Maybe at this moment you study with Professor Vitun, right? About the pressure drop over or something that is related to the turbine, if I remember correctly, right? So that is how we utilize the knowledge of numerical approach to numerical experimentation to conduct the experiment. It's very useful, as you may see, but then there are a lot of things going on inside the software. And as you are engineer, you are not just the operator who do the simulation by just clicking. You need to understand so that in the future you may be able to develop your own or make this program proceed to the much more efficient to become a much more efficient software, something like that. So develop it, improve it, something like that. So it's very important because you are an engineer, you're not just an operator. You need to know that maybe you will encounter a very complex problem in the future, and then there will know some commercial software to solve the governing equation that you are facing in the problem. So you need to And that happens all the time. That happens all the time. So I just want to like stress this again, that it's very important thing, and it's the key of the future, because the computer will like getting more advanced and advanced. So please try to enjoy. And then we have to know about the thing that is called free stream velocity. Free stream velocity is basically just the velocity that is sufficiently far from the body. So somewhere far away is the velocity at that point. So I don't think it's very important here. Okay, so the fluid velocity at the surface of the body, like the airplane here, will start from zero at the surface, and then they will like increase little bit by little to reach the free stream velocity that is like far away from the surface. So it's kind of a velocity that the velocity of the fluid that was not influenced by the body. So basically that is the wind speed for this case. Okay, so then we have a drag, very important. I just like assign one of my research group, I think I should call it like that. So there were 3 students trying to like create a bicycle, electric bicycle. So I asked them, okay, you need to sizing the motor, you need to sizing the battery, but not just go to Shopee and then like make a search, okay, e-bike battery, and then you click to buy. No, it's not like that. You are an engineer, so you need to like design. You need to design and you need to make a decision which motor you are going to use. Not just that, make a comparison with the actual e-bike, but your own design, your own condition that you want to create the e-bike, something like that. So in that kind of calculation, there was some involvement about the drag. Because the drag is, as you know, is dragging when you drive some car, you drive a bicycle to like not in the opposite direction with the wind flow. So it's very important. You need to design. So then how could you know that the coefficient of drag force in the bicycle that you select was right? No, you cannot know. Each car, each bicycle have different CD. So in order to evaluate for the CD of the car, this is what people do. In the real experiment, they would like create a model like this, the real one, and put it in a wind tunnel, and then make a flow over the car, and then they like measure the force that was pushed back because of this wind, like this. But then you can imagine that, let's say I want the student to do this. They need to have the wind tunnel. They need to buy the actual bicycle first. So no chance for modification of your bicycle, right? So no chance of the design, something like that. So you need to buy the actual one and then put it in the wind tunnel and find the CD. No, it's not like that. We start from doing it in the computer software, ANSYS, as you may know. So to calculate for the CD, and that is really helpful. And you utilize the CD filter with your calculation to sizing the motor, to sizing the battery. Okay. And then we have the lift, right? The drag and the lift, and we also have the skin friction. Okay. Not so important. I think the lift is the force that move the body in the yeah, it's not so important. It's like lifting the body. And the skin friction is just along with the fall. They generate the shear force, and that shear force will like dragging the car back like that. So yes, here is how you like calculate for the drag coefficient. If you have the experiment, you measure the force. You cannot measure, let's say you cannot measure the CD. This is the way that you need to think about your the experiment. You cannot measure CD, but you can like indirectly calculate for the CD from the force that you measure. So here is basically 1, 2, 3, 4 different parameters that can influence your CD. Okay, so if let's say like the FV is the measure value, right? It could like the error could happen due to the experimental apparatus or the scale of like the accuracy of the apparatus. Again, for the load, this is very important. As you know, the load or the density change with the pressure, with the wind speed. If the wind is too strong, the pressure change. How could you deal with it? So there are so many parameters that can like have an influence on the CD. And also their surface area. I don't think like measuring their surface area is also difficult. Not just very simple that everyone can do. They require some sophisticated method as well to measure the frontal area and put it here. And the frontal area is okay if you have the drawing on the CAD in a CAD software. You probably like make analysis and obtain the A here easily. But to measure it experimentally, I don't think it would be that easy. So a lot of things was involved in this CD and influenced. And I think at this moment, the car that they claim to have the lowest drag coefficient and was sold commercially is the one from Tesla. I just saw their advertisement a few days ago in their EV course. I think some of you all also like registered for the EV course. And yeah, at that time, it's the first time that I realized that they can get the CD to really, really low value, around like 0.2, which is quite low for the car. Actually, CD is much higher. And I think maybe last year, the CD of Tesla car is around 0.24, which is already lowest at the time. They still like try to like achieve the further improvement. And so now they achieve with their CD equal to 0.2. Yeah. So this is how the engineering works, right? So we try to improve all the time. We try to create something new that is better than what we have at this moment. So if you like keep on studying, I think you probably have a chance to apply for a job at Tesla Motor or maybe like VinFast Motor in Vietnam. They are very famous now, and they like supply a lot of car to Europe. So there is a lot of company all around the world. And when you graduate, you have a chance to work with them. Okay, so the city here is actually the one that already include the skin friction drag and the pressure drag. And sometime for the not sometime, but yeah, for the flat pay, when the let's say this body rotated, and then it becomes like a rotated for like 90 degrees. So the drag will have only can be approximate to have only the skin friction drag because there were so very little surface area to say that the pressure drag is significant. Okay, so for the low Leno number, most drag is due to the friction drag. Okay, friction drag is proportional to surface area. Yes. And the pressure drag is proportional to the frontal area and the difference between the pressure acting on the front and the back of the body. And then, okay, pressure drag has a really high impact when you are having a blunt body like this. Here is the tennis, right? Tennis ball. Oh yes, this is a very important thing because I'm really interested in this one when I was a bachelor student. I think in fluid mechanics, there was one figure. If you can remember, you can like go back and have a look of the figure of that figure. Is the figure showing the CD, I think, or maybe the force generated by the drag, and then they compare between two things. I think one of them is the golf ball, and another one probably the tennis ball. They compare the CD at different speed, and then they have the explanation of why. Have you like ever think of why the golf ball have to have a like kind of a hole? No, not a hole. What does it call? All over the surface. So it's not smooth. There were some like a little bit of valley and the peak all around the golf ball. Right? That is all to reduce the drag. I really surprised about this. I'm not sure like you remember it or not, but this is really surprised me, and I really want to like make a experiment by myself since I was a bachelor student. But still, how many years passed? Around 8 to 9 years passed. Haven't did it yet. I haven't done it yet. So I think it's quite kind of very interesting of how people trying to like reduce the drag using the engineering idea to make the golf ball can travel farther than like a very smooth surface could generate it. Okay, so now we have the more separate region is mean the more pressure drag, and the separate region is this region. Is this region. So it's the region of low pressure behind the body. There will be some recirculating and backflow occur behind here. I think I have some some kind of video to show you. I did it when I was a bachelor student. Not so, it's nothing to show, but I think it's still maybe like help you to feel more into the, where can I find it? Feel more into the computational fluid dynamics. Wait a second. Finding. Hold on. How can I find a video? Okay. No. No. Oh. I just don't know how to access to the video that I post for a long time ago in a Facebook. Oh my God. I don't know. Don't realize that. Okay, fine. Maybe next time. Maybe I can like have a search on the internet, on the YouTube, would give you an idea of the flow as well. Okay, so yes, this is the one. I did it something like this. So you can like simulate this kind of, how to say, this kind of thing that generate to you that is generate through the flow. So this is actually the wing of the airplane. But this is not so like interesting in my opinion, because like the speed of the flow is very small. I did it with something. Okay, here is also the one that maybe you like learn about it.
Hey guys, well,
wait a second. Okay. So
smoother image.
is the one common it's called like when you like have a flow, right? Flow to a cylinder like this. At a certain Reynolds number, it will generate a wake like this, like a snake. I'm not sure if they have a animation or not.
Here we're gonna do the same thing. 3 seconds, but after now the animation, what we're gonna do is we're gonna reduce the number of contour. Here is click on animation, and then we're gonna click on time steps. You could change. What you're gonna do is hit play, and then it'll start saving each frame. So we're gonna hit play. Oh, I already have a movie there called that, so we can call it low. Hit play. So contour 1 loading. So now it's actually loading each frame and saving it as this WMV file. So what will happen is if you either stop it or you wait for it to finish, you can go into this folder and find the movie file. So I'm not going to wait for this to show the animation that was created.
And it is like this.
You can see here.
So it's kind of very interesting phenomena for me.
Effect. And I stopped the simulation after about 2.
Yeah. So maybe you can like, because you already have answers on your computer, right? Maybe you can do it by yourself. Just like make a search, learn about it a little bit, and try to do it. And you will learn more about the thing that is like happen in fluid dynamics. Okay, so now we start about the heat transfer. The heat transfer is, of course, we have the Nusselt number. I'm not sure if you can remember Nusselt number or not, but Nusselt number is the ratio between the heat transfer coefficient and the heat conductivity, right? Not sure you remember or not, but we learned it last time. And as you can see, most of the time, the Nusselt number vary along the surface. So that is why this is a relation of x. Okay, but this is for the local Nusselt number. So we have the Nusselt number as a function of x and Reynolds number and Prandtl number. But then for most of the time, if you like have a look at their publications, which mean the academic article, I cannot remember already if I assign you guys to find the academic article this semester. I'm not sure if I have an Alzheimer or not.
You already assigned your teacher,
Okay.
and also assigned the group already.
Okay, that is really great. Thank you. I cannot remember exactly like what I talked like maybe yesterday. Way too busy to remember things, but yes, if you have a look at maybe at this moment there were still some people still interested in proposing the empirical formula like what I mentioned. So they need to create this kind of formula and show you, and you can find the details in those academic articles. And then most of the time people found that the Nusselt number is a function of Reynolds number and Prandtl number in this way. So they usually like present it in this form. And this form is just the average Nusselt number. So it's the number that you obtain from average all over the region, all over the surface. Okay. Then there is some very important thing that you need to know, which is the flame temperature. Flame temperature is the temperature that you utilize in the calculation. You need to know it. It's just the mean between the surface temperature and the fluid temperature. So it's pretty simple. And then for the friction coefficient, if you like have a friction coefficient as a function of x, you can like make an integration and then divide it by L, because when you like integrate it over L, it's like you have the CV of all L, right? Sum up together. So divide by L would make the average. And this is very simple thing. I mean, like, I did teach this. I did talk about this in I think electric vehicle. And then a lot of people don't know that this is how we do the average. If we have a function of something, I really don't understand. Like, I think you learn it in maybe like mathematics 2, calculus 2 or calculus 1, whatever. But it's like, it's not calculus 3. And it's just the definition of summing up and divide by L. And this is also true for something else as well. Like H, you can do it by like perform the integration and divide it by that length. So with all of this going on, we can like in the end write the heat transfer rate in a very simple form. like this. Q equal to HA delta T. Okay. So now we have a flow that flow parallelly over the flat plate. All right. So they're talking about a transition from the lamina to the turbulent. And I think this means the distance used to turn from lamina to turbulent. That what is the thing that they are talking. So it depends on surface geometry, roughness, upstream velocity, surface temperature, and type of fluid. So there are so many things going on. There are so many parameters that can influence the flow. Can influence if the flow is the lamina or the flow is the turbulent. And the parameter to indicate this kind of stuff was usually referred to the Reynolds number. And the Reynolds number here is the Reynolds number at the local. So local Reynolds number because it depends on the X. Okay. So yes. And they generally accept that the flow will turn from lamina to turbulent. No, it's not to turn. It's mean like the point that we can consider that here from now on is the turbulent is this one when the critical Reynolds number equal to 5 times 10 to the power of 5. So it means that here would be probably the lamina flow, but then the lamina keep changing into the transition flow and then become fully turbulent at this point, at the point of the critical Reynolds number. Okay. But yes, as I think I mentioned about it, that this kind of number is not the exact number that kind of a Bible for you, but it's something that you observe experimentally. It can vary. That is what I mentioned. So that is why they also note here that Reynolds number can vary from like 10 to the power of 5 to 3 times 10 to the power of 6. This is really large. Okay. So now here comes the thing that maybe you don't like. So equation. Oh yes, I did talk about heat transfer when I learned it in my bachelor study, right? So actually at that time we have an exam on site, right? Is need to be a subject for it need to be a subject, the exam that held by allowing student to be able to open the book, because no one can really remember all of this, you know. So there are too many stuff. That is why. And here it's very simple. I will try to explain to you. So the delta here is the boundary layer thickness. Not sure if you remember or not, but boundary layer thickness, we talked about it last session, 0.99, right? The point of 99% to reach the upstream velocity, or point of 99% to reach the surrounding temperature. So it can be evaluated using this relation. If the flow is laminar and the flow is over the flat plate, like this, and that flat plate has to have the temperature constant all along the plate. So it's really unique. This one is really unique to the problem. Again, here the lift force as well. No, the frictional force, the frictional coefficient as well. And it's work with only the Leno number lower than 5 times 10 to the power 5. And here we have for the turbulent region, so it worked with 5 to the power of 5 to like 10 to the power of 7. Did I say 5 to the power of 5? No, I mean 5 times 10 to the power of 5. Oh, yeah, whatever. But it's really limited to this region. Is the region that it can like predict accurately. If you face the fall that the turbulent, the Leno number is beyond this point, you need to find some other relation. Is this relation, this limitation was generally from the experiment, because they only conduct the experiment in this region, so they can say that, okay, this relation is valid in this region, but beyond this region, no, I don't know what is going on. You need to find it yourself. That is what they are talking. So now So now we have the C of X, right? So we perform the integration in order to have the average of the friction coefficient. Then we end up with the friction coefficient like this. This is the average over the laminar region and the turbulent region for the flat plate. Okay. So if you don't have a problem here, then we can skip it to here. So we can also like find the combined frictional coefficient of laminar and turbulent flow by like performing the integration, like starting from 0 to critical region. Do you still remember critical region? So where the Leno number equal to this one. So we perform the integration to that point, and then we perform another integration and add them up and make the average. And then we end up with having this relation, which is the friction coefficient average over entire plate. Okay, because this solution is really unique, because it's not that all application would have to consider both laminar and turbulent flow, but because the plate is way too long, that's why we need to consider both phenomena. If the let's say that if the plate is not so long, it's very short, so you could end up with having only laminar flow or turbulent flow. And you can see that in this relation, it will reduce to this, right? This is only like when the Leno number is really high. It's happened when the when the critical region is very small. So it will reduce to this one, which is resemble this part. And as you can see, not only that we have this relation to explain the thing that is going on in the flow, in such flow. But like this is the one that they obtain from a very smooth surface. So it's not that smooth, but you like try to make it as smooth as possible. So then you can like make an assumption on your experiment and say that this frictional coefficients works well with a smooth surface. And then they comes slitting. In 1979, they performed to find the friction coefficient in in the left surface, and they provide this equation. Just that. So here epsilon is the surface roughness, and L is the length of the plate in the flow direction. Just subtract it, and then you would have the CF. But all this kind of equation have limitation. You have to have a look in the books or in some article. What is their limitation? Let's say this CF has the limitation only it works well only when the epsilon over L is larger than 10 to the power of -4, and the Reynolds number higher than 10 to the power of 6. So it's different from this. It's very unique to every single equation, and you need to carefully read about it. Okay, now because we know how to create the frictional coefficient, right? We move a little bit next to the heat transfer coefficient. They performed the experiment. Some people did it, and they found that the local Nusselt number at location X can be determined using this equation. So it depends on the Reynolds number at that point. Okay, so using this, we can calculate for the local H at that point. So as you can see, the local H vary with along the flow direction. Okay, the turbulence as well is the same, but then here you need to not only have a look at the Reynolds number that they works well. You still have to see if the Prandtl number that you are of the problem that you are facing is right like this or not. Okay, so yeah, this is for the isothermal and smooth surface. Then, of course, you perform the the integration, right? Just like just now. And then we obtain the average value of the Nusselt number so that we can try to simplify the problem. And then we have the H. This H is the average one. And this average H will be put into your equation, the Q equal to HA delta T, to calculate for the heat transfer. And this is the same. We perform with the same procedure with the friction coefficient by integration in both laminar and turbulent flow, and obtain this equation. Yeah, we obtain it from something like this. And then they also provide some other relation, for the Prandtl number starting from 0.6, right? But then if we consider some other fluid like a liquid metal, when they flow slowly, right? But then when you already also have the heating surface connected to the metal, you will see that they transfer their heat very quickly because of their K, right? The heat conductivity. So we need some other relation that is not close, not the right one, not the same with other fluid. And we found that for the liquid metal, the Prandtl number is pretty low, right? The Prandtl number is pretty low, but actually, I think here in the okay, here it's here Peckley number. So the Prandtl number is low, and then some people do the experiment and obtain this equation, and then again, there's some guy who try to do the single relation that apply to all fluid. And they, of course, do the curve fitting, and they propose that this relation is very accurate, like have a percent of error of less than 1%. So, yes, this is the other one. And talking about, okay, so there is another dimensionless number created by Peckley, their friends. So, they perform some experiment and then create this Peckley number, which is defined as the Leno numbers times the Prandtl number. So we obtain the Peckley one. And you need to see if this one works for which Peckley number, and it indicates in the books that it works with the Peckley number higher than 100, something like that. So you need to be careful. I think this is the last slide. Okay, last two for the thing that I want. Where is it? Where? Okay. It's back. All right. So, because just now we only limit our consideration to the plate that has the uniform distribution of temperature, and there is no unheat starting length. No, this, I think it's called zeta, right? Zeta, something. I'm not sure how we call this Greek letter. Maybe zeta, something. Not zeta, but yeah, pronounced by the Z here. Okay, but whatever. I'm not sure if it's correct or not. Just forget it. But then to account for this unheat starting length, there are some other people again try to propose the relation, and here is that relation, much more complex than the previous ones. So you just it's nothing. You just substitute the equation, the parameters into your equation, and then you will find. Okay, and you will be fine. And then they perform again because as you can see, this equation seems very complex. So they perform their numerical integration, not the exact integration. They perform the numerical integration and obtain this relation. So we can find the H using this equation in the laminar and turbulent. Okay, so now because we consider the case for a very uniform temperature surface temperature, right? Then they extended to some other boundary condition. This condition is like, okay, it's we have a very uniform heat flux. So instead of like putting it on the surface that we held the temperature constantly, we put it on the surface that we held the heat that we supply on the surface constantly. So it's different thing, but so it's lead to different equation. But then this is not so important. So the whole idea of learning all these relations is that when you obtain the Nusselt number, after obtain the Nusselt number, we calculate for the h, and then we supply the h into our calculation. It's all about finding the h. Okay. Any question before we like start to do some exercise or see some example? No, nothing. Cool. Good then. Okay, so let's do it. You need to submit this one as well, okay? But I will show you. I will guide you like every step, but then you need to submit it into the assignment that I will create. Wait a second. Okay. So let me create their assignment first. Starting with Google Classroom. And then we do the heat transfer and then create the classwork. Okay, so now when you like do the complete like try to submit the classwork, would you please like use the ID, the order that you can find in the IEG here. Use it in front of your file that you are going to submit to me. I think it would be really helpful for me to grade your application. Okay? To grade your homework, to grade your classwork or whatever. But for this classwork, so we need to submit it by 12 o'clock today. Let's see, we have classwork now would be number 3. All right, just follow me. We have the engine oil at 60 degrees Celsius flow over the upper surface of 5 meters long clip and has a temperature of 20 degrees Celsius and flow with a velocity of 2 meters per second. So determine the total drag force and the rate of the heat transfer per unit Y over entire plate. So now we have to go have a look for the frictional coefficient. So frictional coefficient, just now they say that is the total, right? total drag force and the rate of the heat transfer. So it means in total, on average, something like that. It means that we need to use one of these equation for the drag. You still with me, right? And then you need to like go have a look if the oil like close to any fall into the which Reynolds number, and then we utilize that one. And again for the Nassau number, so Nassau number start here. So Nassau number probably this one, I'm not sure, or maybe oil can be treated as the Prandtl number, I'm not sure, or maybe yeah, we utilize this one. I'm not sure as well. But then there are so many relations here. So first thing, you need to check the properties of all this. Okay. So here, the film coefficient is the one that we will use to evaluate for the properties of the engine oil. Not 60 and not 20, but the film coefficient. And the film coefficient is the average between the two, which is 40. So we go have a look at the back of the book, right? And see the table. Okay. So now, we have, okay, here is the British unit. Up. So just now it's 13. Okay, here is the property of the liquid, right? And you can see this is the thing that you can obtain. There are so many things. Let me copy it. So many things were going on. And then we evaluate it at the 40. Like this. Okay. So luckily, everything is. Let me delete all of this first. Luckily, we already have the information about 40 degree here. Let's say if the flame temperature is not 40 but it's 55, what will you have to do?
Interpolate.
Of course, yeah, interpolate, right? You are correct. Just like that. So now we can, where is it? This one, right? So now we just need to extract the thing that we want in our calculation. Okay. So as you can see, let's say for the friction coefficient, you need the Reynolds number. Okay. So you need a Reynolds number. It means you need the Reynolds number relation. Like this, right? But this is the local Reynolds number. It's not so different. We just utilize the characteristic link. And in this case, for the flat plate like this, characteristic length is 5. It's the length here. Okay. So now what you need to have is the law, right? Oh, you don't need it. Maybe the velocity and the kinematic viscosity, and the L you already know. So the V is here, which means that, let's wrap it up. For the Reynolds number, we have the V, VL, and the nu, right? Not this one, this is epsilon nu. So is V, which is 2. We have L, which is 5. And we have the nu, which is 2.485 times 10 to the power of minus 4. Okay, we're good now. So just do some calculation. Wolfram. Okay, so 2 times 5 over 2.485 times 10 to the power of minus 4. Then you have, oh, sorry. Okay, now we have 40,000, right? So just now, 40 something.
Teacher, can I ask you something?
Yes.
I'm wondering, the we, right? We use for the 40 degree, right?
Huh?
Or 60 degree.
The new?
Like the V, the smaller one.
Okay, you mean the new, right? New.
Yeah. What?
It's new. It's Greek letter.
And which one
40.
that 40, right?
Yeah, you should evaluate everything that relate to the fluid using the film temperature, which is the average between these two values, 60 and 20, which is 40.
Okay, I got it.
So now you see that the Reynolds number is 4 into lamina. Right? This is pretty simple. I think we still need to utilize it later, but okay. We need to find the friction coefficient first. Friction coefficient. Yeah. CF to 1.23. Then, oh no, not this one. No. Okay. Real number L power of 1 over 2, like this. So it's pretty simple because we only need to submit the Reynolds number. into the equation. So 1.33 over, oh sorry, oh no, not like that. Okay, and then to the power of 1 over 2. Oh no, again. Why do I have space all the time? Okay. Then you just use 1.33 over 241 and power of 1 over 2. Okay, this is the result. That's it for the first question. For the second question, oh, okay, drag force. Right? Drag force, we need to utilize drag force. Okay, it's the same one, the same equation. I think they didn't put it here, but yes, it's actually the same equation with this one. Ah, yeah, right. Let's do it. Drop a bit. Okay, so now we need to find, here is the average friction coefficient. So now we are trying to find the drag force. FD, right, equal to CF. Actually, I love to express it. We have frontal area, and we have because we use A here, and V to the power of 2, like this. It's just a drag force, so we just utilize it, CF. And then we have A, which you can, I think, because they're talking about the unit wide, right? Which is 5 times 1, so just 5. So just consider that only a unit of length at that area. So then we have a law of 876. And then V, right? 2 to the power of 2. Okay, so now we can calculate both. Times 5 times 876 times 2 to the power of 2. And here is the answer. Okay. All right. Now we need to find the Nusselt number. So we know that the flow is laminar. This is pretty simple. We just utilize the laminar relation here. Okay. Laminar relation. Then what you need in laminar relation I like this. So we have the Nusselt number, which is h times L over k equal to 0.664 times the Reynolds number to the power of 0.5. And then times the Prandtl number. Prandtl number at 40 degrees is this one. So 2962 to the power of 1 over 3. And then we have the K. K at the 40, which is 8 here. Am I correct? No, sorry. Here. 0.1444. And we have the L, which is 5. And that's it. Now you can evaluate for the H. Okay, I think I can delete this one now. Then do it. H times 5 over 0.144 equal to 0.664 times 2.1 times. Okay. All right. I think everything is solved for the H. No, H is a unit. No. Let's call it X. Okay, so X equal to this value. Okay, then we need to evaluate for the rate of heat transfer. So it's just the Q dot equal to the average of heat transfer. Oh no. Average heat transfer coefficient times the surface area and then times the delta T. Okay, so the delta T here is the T between the flow, which is 60 and 20. This is just to make the value to be positive. That is why we put it like this. But it makes no difference. It's just the indication for the direction. So whichever you like, just use it. So now, time it by 5, time it by 20 minus 60. So this is the answer for the first one. So here is the answer. Here is also another answer. Okay, any question? No? Pretty simple, right? So the other one is also the same, but requires some idea. I think if you have a look at the textbook now, you will know what I want you to do. So please take your time. I think like we have about 90 minutes. Please try to complete this by yourself. Okay. I will stay here. If you have any problem, just ask me. But please try to do it by yourself. This one. Okay. I think it's not so difficult, but it's kind of the problem that would help you to link the idea from the, the previous knowledge that you already learned. So you can calculate for this type of problem using the circuit analogy, right? Circuit analysis, because it's the heat conduction that exposed to the convection. There's two convection here, which is airflow outside, and here is the inside the engine. And then you see that the inside of the engine was already provide some information, but for the outside, they don't provide the information. So what you need to do is to find the edge of the outside. And because they already provide us the K of insulation and engine cover, so combine them all, we can calculate for the heat transfer rate, right? But what do they ask? They also suggest to evaluate all the air property as 120. So basically is that they have an engine, right? So they want to keep the temperature down to below 180. So they ask if this condition would lead you to the temperature low at the surface lower than 180. Just that. No, 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 no. Airflow here is the cover of the engine, and here is the inside. Okay, so if you read until here, they will say that the plant supervisor, so an engineer, suggests that maybe they like increase their blower capacity to increase the flow rate. Okay, so they can like have the temperature below the point that they want. So basically, it's just air cooling, just like turn on the fan in order to like to remove the heat. So it's not engine oil. But you will see that this is quite tricky because like at first they provide you the velocity of 7 meters per second, right? But here, if you read to this point, they say that supervisor suggests to increase the air velocity by 10%. So the value that you use should not be 7, but it's something that is bigger for 10%. Okay, I'm not sure if you are able to make it on time. Probably yes, I think.
Teacher, could you
Extend?
make this? Could you take this example, this question as the homework?
Oh, really? Why?
I think we couldn't do it on time. I just couldn't do it. I need to think
Oh,
more.
really? So what is the problem here? Let me know. So where is the problem?
Let me see. What should I say? Just like I'm not sure.
Do you still remember the
Yeah.
one in the chapter 3 that we utilized the circuit analysis?
Yes.
So that is the same. You can just utilize that one. So is there a resistance here connected to the resistance here and here, and then we have another resistance here. So 4 resistance in series. And then you just need to find the surface temperature. But then if you like substitute all the value into the equation that you created for resistance in series, right? You will see that one thing missing. That thing is the temperature, the heat transfer coefficient of the airflow. So you need to find the heat transfer coefficient of the airflow, and that could be achieved using this relation. This kind, not exactly this relation, but we should utilize this kind of relation to find the edge. But then you will know which equation to be selected by like calculate for the Reynolds number, and the Reynolds number here need to be calculated from 7.7 meter per second. Because here the supervisor suggests to adjust the capacity to increase the velocity by 10%. That's it. And if you are able to create to like find the edge, I think you will like have no problem in solving this problem. Okay, all right. We need to finish now, so just submit what you did in the Google Classroom, and then enjoy your holiday. We have no homework, so I think that is good thing for you. And then we meet again on next week. Okay, so have a good day. Bye bye.